MAP Fundamentals. The core concept. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are going to demystify the mathematics behind MAP, which stands for Mapping of Address and Port. The fundamental question we will answer is this: how does a customer's equipment know which IPv4 address to use and which ports are valid without asking anyone or looking anything up in a database? The answer is elegant and powerful. The information is mathematically encoded directly into the IPv6 prefix that the customer receives from their ISP. Think of it this way. Traditional systems, for example, DS Lite, work like a code check at a restaurant. You hand in your code, they give you a numbered ticket, and they maintain a list that says ticket number 47 corresponds to the blue code on hanger 23. Later, when you return the ticket, they look up number 47 in their list to find your code. This requires maintaining and consulting the list every single time. MAP works completely differently. It is like encoding information directly into the ticket number itself. For example, ticket number 4723 might mean floor 4, row 7, position 23. Anyone who knows the encoding scheme can figure out where the code is without consulting any list. MAP does exactly this with IPv6 addresses. The IPv6 prefix that a customer receives contains what are known as EA bits, which stands for embedded address bits. These are specific bit positions within the customer's IPv6 prefix that encode two pieces of information. First, which IPv4 address suffix the customer should use, and second, which PSID, or port set identifier, they have been assigned. The PSID then determines which ports they are allowed to use. Both the customer's equipment and the ISP's border router can extract these EA bits and perform the exact same calculations to determine the IPv4 address and port range. No communication is needed. No database lookup is required. Just pure mathematics that both sides execute independently to arrive at the same answer. IPv6 address structure and bit positions. Before we can extract the EA bits from an IPv6 address, we must understand how IPv6 addresses are structured at the bit level. An IPv6 address is 128 bits long, which we conventionally write as 8 groups of 4 hexadecimal digits separated by colons. For example, 2001:0DB8:0013456000000000000000. Each of those 4-digit hexadecimal groups represents exactly 16 bits, because each hexadecimal digit represents 4 bits. When we talk about bit positions in an IPv6 address, we number them from 0 to 127, starting from the leftmost bit, which is the most significant bit. So bit 0 is the very first bit on the left, bit 1 is the second bit, and so on until bit 127, which is the very last bit on the right. The prefix length, indicated with slash notation like /56, tells us how many of these leftmost bits constitute the network prefix versus the host portion. A /56 prefix means the first 56 bits are the network identifier and the remaining 72 bits can be used for individual devices. Now here is the critical insight for MAP. The EA bits are not aligned to the convenient hexadecimal group boundaries that we see when we write out the address. The EA bits occupy specific bit positions that are determined by the MAP rule parameters, and these positions often span across the boundary between two hexadecimal groups. For example, if the MAP rule specifies a /40 prefix and customers receive /56 prefixes, then the EA bits occupy bit positions 40 through 55. Looking at our example address, hex group 3 contains bits 32 through 47, and hex group 4 contains bits 48 through 63. So the EA bits from position 40 to 55 include the last 8 bits of group 3 and the first 8 bits of group 4. This is why we cannot simply look at a hex group and call it the EA bits. We must carefully extract the exact bit positions specified by the map rule. Extracting EA bits. Step-by-step process. Let's walk through the complete process of extracting EA bits from a customer's IPv6 prefix using concrete numbers, so every step is crystal clear. Our customer has been assigned the IPv6 prefix 2001:DB8:1234:5600:/56. The ISP's MAP rule specifies that the rule IPv6 prefix is 2001:DB8:1234::/40. The EA bits length is 16 bits, and the user prefix length is /56. Step 1 is to identify where the EA bits are located. The rule prefix is /40, which means bits 0 through 39 come from the rule and are the same for all customers. The user prefix is /56, which means bits 0 through 55 are the customer's network prefix. The EA bits are the bits that come after the rule prefix and before the end of the user prefix. Therefore, EA bits occupy bit positions 40 through 55, which is exactly 16 bits as the rule specifies. Step 2 is to convert the relevant portions of the IPv6 address to clearly see these bits. Let's write out the hex groups with their bit positions. Group 1, which is 2001, occupies bits 0 through 15. Group 2, which is 0db8, occupies bits 16 through 31. Group 3, which is 1234, occupies bits 32 through 47. Group 4, which is 5600, occupies bits 48 through 63. We need to extract bits 40 through 55. Bit 40 through 47 are in Group 3, and bit 48 through 55 are in Group 4. Now we must extract precisely these bits. For Group 3, the hex value 1234 in binary is beginning with 00 ending with 00. We need the last 8 bits, which are beginning with 00 ending with 00. In hexadecimal, beginning with 00 ending with 00 is 34. For Group 4, the hex value 5600 in binary is beginning with 01 ending with 00. We need the first 8 bits, which are beginning with 01 ending with 10. In hexadecimal, beginning with 01 ending with 10 is 56. Combining these, our EA bits value is 3456 in hexadecimal, or 0x3456. Calculating IPv4 address from EA bits. Now that we have extracted the EA bits value of beginning with 0x34 ending with 56, we need to split this 16-bit value into its two components: the IPv4 address suffix and the PSID. The MAP rule tells us that the PSID length is 8 bits. Since the total EA bits length is 16 bits, this means the IPv4 suffix uses the first 8 bits and the PSID uses the last 8 bits of the EA bits value. The EA bits value 0x3456 is a 16-bit number that we can view as 2 bytes. In hexadecimal, we can write this as 0x34 followed by 0x56. The first byte, 0x34, represents the IPv4 suffix. The second byte, 0x56, represents the PSID. Let's focus on the IPv4 suffix first. We have 0x34 in hexadecimal. To use this in an IPv4 address, we need to convert it to decimal. The hexadecimal value 0x34 means 3 times 16 plus 4, which equals 48 plus 4, which equals 52 in decimal. So our IPv4 suffix value is 52. Now, we combine this suffix with the rule IPv4 prefix to construct the complete IPv4 address. The map rule specifies that the rule IPv4 prefix is 203.0.113.0/24. A /24 prefix means that the first 24 bits, or equivalently the first 3 octets, are fixed by the rule. Those three octets are 203, 0, and 113. The fourth octet, which represents bits 24 through 31 of the IPv4 address, is what we calculate from the EA bits. We calculated the IPv4 suffix as 52, so the fourth octet is 52. Therefore, the complete IPv4 address is 203.0.113.52. This is the public IPv4 address that this customer must use for all their internet traffic. The customer's equipment calculates this address mathematically from their IPv6 prefix, configures it into their NAT engine, and uses it without ever needing to ask the ISP or look it up in any table. Calculating PSID and port range. We now turn to the second component of the EA bits, which is the PSID, or port set identifier. Recall that our EA bits value was 0x3456, and we used the first byte, 0x34, for the IPv4 address calculation. The second byte, 0x56, is the PSID value. Converting 0x56 from hexadecimal to decimal, 5 times 16 plus 6 equals 80 plus 6 equals 86. So, our PSID is 86 in decimal. The PSID determines which subset of the 65,536 available port numbers this customer is allowed to use. There are two common methods for calculating the port range from a PSID: the contiguous allocation method and the algorithmic allocation method. Let's start with the contiguous method because it is simpler to understand. With contiguous allocation, we divide the available port space into equal-sized blocks and assign each PSID one contiguous block. Here is how the math works. The total number of TCP or UDP port numbers is 65,536. Numbered from 0 to 65,535. However, ports 0 through 1023 are reserved as well-known ports for system services, so we should not allocate them to customers. This leaves us with 64,512 usable ports, from port 1024 to port 65,535. The MAP rule specifies that the PSID length is 8 bits, which means there are 2 to the power of 8 equals 256 possible PSID values, numbered from 0 to 255. We divide the 64,512 usable ports among these 256 PSIDs. That gives us 64,512 divided by 256 equals 252 ports per PSID. Pages SID number 0 gets the first 252 ports, which are ports 1024 through 1275. PSID number 1 gets the next 252 ports, which are ports 1276 through 1527. And so on. For our PSID of 86, we calculate the start port as 1024 plus 86 times 252. That is 1024 plus 21,672, which equals 22,696. The end port is 22,696 plus 251, which equals 22,947. So with the contiguous allocation method, PSID 86 gives this customer ports 22,696 through 22,947, a total of 252 ports in one continuous range. Algorithmic port calculation method. The algorithmic port allocation method distributes ports differently by using bit pattern matching rather than contiguous ranges. With this method, a port number is valid for a particular PSID if specific bits within the port number match the PSID value. The MAP rule specifies two parameters for this: the PSID offset and the PSID length. Our example has a PSID offset of 6 and a PSID length of 8. Here is how the algorithm works. A port number is represented as a 16-bit integer. We extract a specific sequence of bits from this port number, starting at the bit position indicated by the offset and continuing for the number of bits indicated by the length. If these extracted bits equal our PSID value, then that port number is valid for us. With an offset of 6 and length of 8, we extract bits 6 through 13 from each port number. Remember that bit 0 is the rightmost or least significant bit of the port number. Let's check whether port 1376 is valid for PSID 86 using this method. First, we convert port number 1376 to binary. 1376 in binary is 000, 0101, 0110, 000. Reading from left to right, where the leftmost bit is bit 15 and the rightmost bit is bit 0. We need to extract bits 6 through 13. Counting from the right, bit 0 through bit 5 are the rightmost 6 bits. 00000. Bits 6 through 13 are the next 8 bits. 0101, 0110. Let's convert these 8 bits to decimal. 0101, 0110 in binary equals 86 in decimal. Our PSID is 86, and the extracted bits equal 86. So yes, port 1376 is valid for PSID 86 using the algorithmic method. This method gives the customer 256 ports scattered throughout the port range based on the bit pattern, rather than one contiguous block. The advantage is that every PSID gets access to some low-numbered ports, some medium ports, and some high ports, which can improve application compatibility. MAPT. Building IPv6 with embedded IPv4 in port. In MAPE, the customer equipment encapsulates the IPv4 packet inside an IPv6 packet and tunnels it to the border relay. MAPT takes a different approach. Instead of encapsulation, MAPT performs stateless translation between IPv4 and IPv6. A critical part of this translation is that the IPv6 source address must embed the IPv4 source address and source port number so that the border relay can extract them later. Let's walk through how the customer equipment builds this special IPv6 address. After performing NAT, suppose the customer equipment has an IPv4 packet with source address 203.0.113.52 and source port 22700. These need to be embedded into an IPv6 source address. First, we convert the IPv4 address to hexadecimal. The IPv4 address 203.0.113.52 consists of 4 octets. The first octet is 203 in decimal. To convert to hexadecimal, 203 divided by 16 is 12 with remainder 11. In hexadecimal, 12 is C and 11 is B, so 203 is CB in hex. The second octet is 0, which is 00 in hex. The third octet is 113 in decimal. 113 divided by 16 is 7 with remainder 1. So 113 is 71 in hex. The fourth octet is 52 in decimal. 52 divided by 16 is 3 with remainder 4, so 52 is 34 in hex. Therefore, the IPv4 address 203.0.113.52 in hexadecimal is CB 007134. Next, we convert the port number to hexadecimal. Port 22700 in decimal needs to be converted. We repeatedly divide by 16 and take the remainders. 22,700 divided by 16 is 1,418 with remainder 12, which is C in hex. 1,418 divided by 16 is 88 with remainder 10, which is A in hex. 88 divided by 16 is 5 with remainder 8. 5 divided by 16 is 0 with remainder 5. Reading the remainders from bottom to top gives us 58AC in hexadecimal. So port 22700 is 58AC in hex. Now we construct the full IPv6 address. The customer's prefix is 2001:DB8:1234:5600. To this, we append the encoded information. One common format places the IPv4 address in the next 2 hex groups and the port in the following group. The IPv4 bytes CB 00, 7134 become hex groups CB00 and 7134. The port 58AC is already a 4-digit hex group. So the complete IPv6 source address is 2001:5600:0000:CB00:7134:58AC. This can be written in compressed form as 2001:B8:123:5600:CB00:7134:58AC. This single IPv6 address now encodes the customer's identity through their prefix, their IPv4 source address, and their source port number. MAP border relay extraction and validation. The MAP border relay receives packets from customers and must extract the embedded information and validate that it is consistent with what the MAP algorithm would produce. Let's trace through the border relay's processing of a packet. The border relay receives an IPv6 packet with source address 2001:D8:1234:5600:CB00:7134:58AC. First, the border relay parses this address to extract its components. The customer prefix is the first 56 bits of the address, which is 2001:DB8:1234:5600:56. The embedded IPv4 address is in hex groups CB00 and 7134. Converting these back to decimal. CB is 203, 00 is 0, 71 is 113, and 34 is 52. So the embedded IPv4 address is 203.0.113.52. The embedded port is in hex group 58AC. Converting to decimal. 58AC hex equals 22,700 decimal. So we have extracted IPv4 address 203.0.113.52 and port 22,700 from the IPv6 address. Now comes the critical validation step. The border relay executes the MAP algorithm on the customer's prefix to determine what IPv4 address and port range this customer should have. From the prefix 2001:DB8:1234:5600:56, the border relay extracts the EA bits at bit positions 40 through 55, which we calculated earlier as 0x3456. Splitting this into components. The first byte 0x34 equals 52 in decimal, giving IPv4 address 203.0.113.52. The second byte 0x56 equals 86 in decimal, which is the PSID for PSID 86. The valid port range using contiguous allocation is 22,696 through 22,947. Now the border relay performs two checks. First, does the embedded IPv4 address 203.0.113.52 match the calculated IPv4 address 203.0.113.52? Yes, it matches. Second, does the embedded port 22,700 fall within the calculated port range 22,696 through 22,947? Yes, 22,700 is greater than or equal to 22,696 and less than or equal to 22,947, so it is in range. Both validations pass. The packet is legitimate, and the border relay translates it to IPv4 and forwards it to the destination. If either check had failed, the border relay would drop the packet as spoofed or misconfigured. This validation happens for every single packet, yet it requires no database lookup, no session state, just the same mathematical calculation that the customer equipment performed. Complete worked example with different prefix. To solidify our understanding, let's work through a complete example with a different customer prefix. Suppose the ISP assigns a customer the IPv6 prefix 2001-DB8:1234:AB00::/56. We will calculate the complete configuration that this customer derives from this prefix using the same MAP rule as before. Step 1. Identify EA bits location. The rule prefix is /40 and the user prefix is /56, so EA bits are at bit positions 40 through 55. Step 2. Extract EA bits from the prefix. Looking at hex groups, group 3 is 1234, covering bits 32 through 47, and group 4 is AB00, covering bits 48 through 63. We need bits 40 through 47 from group 3. The hex 1234 in binary is beginning with 00 ending with 00. The last 8 bits are beginning with 00 ending with 00, which is 34 in hex. We need bits 48 through 55 from group 4. The hex AB00 in binary is beginning with 10 ending with 00. The first 8 bits are beginning with 10 ending with 11, which is AB in hex. So our EA bits value is 34 AB in hexadecimal. Step 3. Split EA bits into components. The first byte is 34 hex, which equals 52 decimal. This is the IPv4 suffix. The second byte is AB hex, converting AB to decimal. A is 10 and B is 11. So AB equals 10 times 16 plus 11, which is 160 plus 11, equals 171 decimal. This is the PSID step 4. Calculate IPv4 address. The rule IPv4 prefix is 203.0.113.0/24. We add the IPv4 suffix of 52 to get 203.0.113.52. Step 5. Calculate port range. PSID 171 with contiguous allocation. Start port equals 1024 plus 171 times 252, which is 1024 plus 43,092, equals 44,116. End port equals 44,116 plus 251, equals 44,367. So this customer with prefix 2001-DB8:1234:AB00::/56 derives IPv4 address 203.0.113.52, PSID 171, and port range 44,116 through 44,367. Notice that this customer has the same IPv4 address as our first example, 203.0.113.52, but a different PSID of 171 instead of 86. This means they share the same IPv4 address but use completely different, non-overlapping port ranges. Customer 1 uses ports 22,696 through 22,947. While customer 2 uses ports 44,116 through 44,367. Both can operate simultaneously without any conflict because their port ranges do not overlap. Summary and key insights. Let's bring everything together and summarize the key insights about MAP mathematics. The fundamental innovation of MAP is that configuration information is embedded directly into the IPv6 prefix rather than stored in external databases. When an ISP assigns a customer the IPv6 prefix 2001:DB8:1234:5600:/56, this is not an arbitrary number. Specific bit positions within this prefix encode the customer's IPv4 address suffix and PSID, which together determine their complete MAP configuration. The calculation process follows a precise sequence. First, identify the EA bits location based on the difference between the rule prefix length and the user prefix length. Second, extract the exact bits from those positions, being careful to handle cases where the EA bits span across hexadecimal group boundaries. Third, split the EA bits into IPv4 suffix bits and PSID bits according to the MAP rule. Fourth, convert the IPv4 suffix from hexadecimal to decimal and combine it with the rule's IPv4 prefix to get the complete IPv4 address. Fifth, convert the PSID from hexadecimal to decimal. Sixth, calculate the valid port range using either the contiguous or algorithmic method. Both the customer equipment and the ISP's border relay perform these identical calculations independently. The customer equipment uses the calculations to configure its NAT engine with the correct IPv4 address and port range. The border relay uses the calculations to validate every incoming and outgoing packet, ensuring that the embedded IPv4 address and port are consistent with what the customer's prefix authorizes them to use. This creates a completely stateless system. The border relay maintains no session state, no binding tables, no databases of customer assignments. Everything it needs to know is computed on demand from the IPv6 addresses it sees in packets and the MAP rule parameters it has been configured with. Thank you for your attendance. Please consider subscribing to the channel.